Yeah, we have seen until now the mechanical devices for measuring force or weight. They are normally meant for smaller range, few kilogram, or for example compound lever mechanism, that is our platform balance, probably it may be 1 or 2 or 3 tons. Suppose hundreds of tons if you want to measure, naturally people go for hydraulic or pneumatic load cells. Hydraulic is for still higher range, medium range is pneumatic load cells. How a hydraulic load cell and pneumatic load cells are functioning, we are going to see 1 or 2 principles. First, the hydraulic load cell, where there is a diaphragm. On the diaphragm, the load button sits there, and below the diaphragm we have got a liquid, incompressible liquid, and which is connected to a pressure gauge, and you have got the chamber, suitable chamber at the bottom, so that when the force F acts on the load button, the liquid below the diaphragm gets compressed because of the deformation of the diaphragm. So for a particular force, a pressure is developed in the liquid, and that is being read by a pressure gauge. Probably it may be a Bourdon type pressure gauge, and that pressure reading is calibrated in terms of hundreds of newtons or few tons, in terms of tons. How do we ensure that the working principle, you can see this signal flow block diagram. Diaphragm plus oil converts this force into pressure. Diaphragm plus oil, force is converted into pressure. This pressure is read in the pressure gauge, and you have got the output signal as in the form of a motion of a pointer over the scale. So that is our XO. So how to ensure the moment you apply a force, it is converted into pressure? For that is achieved by having a initial pressure. We have got initial pressure of say 1 or 2 bar. It's of the order of 0.2 bar. I mean 2 bar pressure, 2 times atmosphere, or 0.2 Newton per millimeter square. A 2 bar pressure is built in. That is our initial pressure. So the pressure gauge may read a 2 bar or some pressure, that is written as 0 input signal, so 0 force, that is will be 204. Further increase can be only from the applied force. So that is a compact unit made up of hydraulic elements. Next we should see the pneumatic load cell. In the pneumatic load cell, we have the principle nozzle, flapper nozzle principle, that is this constitutes a flapper nozzle principle, is made use of in the pneumatic load cell. It is because the air, compressed air is can be compressed. It is a compressible medium, whereas liquid is incompressible. So this is simple setup, whereas with pneumatic air or any gas, since the fluid is compressible, we are using the flapper nozzle principle. So this is the flapper nozzle principle. It's written there. Fixed nozzle, no. Flapper nozzle principle. So that is being explained before we go to that load cell. See, here we have a fixed nozzle and variable nozzle in the form of the imaginary cylinder, extended, this nozzle being extended in this gap, that is the variable nozzle, and in between these two fixed nozzles we have the pressure gauge, that is a chamber pressure is measured by a pressure gauge. Now the distance between the end nozzle and the flapper, this is a flapper which can rotate or move, varying the distance in front of that tip nozzle, and the chamber pressure in between these two fixed nozzles, we have got supply pressure. It is of the order of 1.2 bar. So sometimes this is usual pressure for the flapper nozzle system. A gas or air, compressed air at 1.2 bar is the supply for this whole instrumentation. So as x varies, the PO varies as per this curve. When x is equal to 0, PO is PS. PO is PS when x is 0. That is when the flapper fully closes, then this pressure becomes the supply pressure. For any other distance x, then it varies. More or less you got some range as linear range in this instrumentation. Anyhow, this is principle. By giving a displacement x, we convert that displacement into a pressure by the flapper nozzle principle. That is what is being made use of in this pneumatic load cell. We have got fixed nozzle similar to that fixed nozzles, and variable nozzle between the extension rod and the bottom wall. We have this variable area. Now, what is this variable area? Pi d. If d is the diameter of this nozzle, tipped nozzle, d is the diameter of the tipped nozzle, pi dx is the cylinder, imaginary cylinder from the tip of the nozzle to the flapper, that is pi dx is the area, and that x will have effect on this pressure PO until this the cylindrical area becomes equal to the cross sectional area of this hole, that is pi, if that is the maximum, that you call, if it is x maximum, that is equal to pi d square over 4. Until this cylinder surface area equal to this cross sectional area of the nozzle, you will have the effect of x on PO. Later on you will not have. That is, both the area are equal. Now you find d pi d, that cancels out. Then you will find x maximum is equal to d by 4. That is the maximum distance one can have. Yeah. So such a distance is given to this extension rod by the diaphragm when the diaphragm is acted upon by a force F. So the force F, see the this block diagram or signal flow diagram, force given to the diaphragm, then diaphragm gets deformed. This deformation is carried to this nozzle, to this opening by this extension rod. So the amount of opening is varied when the diaphragm deforms. That is our variable area, analogous to variable nozzle. So this distance is converted, because this is fixed nozzle, this is variable nozzle. In between these two nozzles, we call it chamber here. So chamber pressure now, that is chamber pressure is a function of the amount of opening here. So the amount of opening is given is nothing but our displacement in the extension rod. So that is proportional to that extension rod. So D is converted into PO by this flapper nozzle system. This PO is read by a pressure gauge, and you got the signal here. So this pressure gauge reading will be calibrated in terms of force we have applied. So known force you can give and calibrate it by having dead weights or something like that. Later on the machine member will act on this, and then unknown force can be read from this pressure gauge, which is calibrated in terms of tons or newtons, whatever it is. So these are the two principles under the hydraulic pneumatic principle. Next we are going to see elastic elements, how elastic elements are made use of in force measurement. A typical elastic element is a ordinary spring, helical spring. This is a helical spring. We call it spring balance. This is a spring balance, domestically used spring, I mean normally used there. So there you will have the hook, and here you hang your weight, whatever weight you want to measure. And from the other end, a pointer is taken. This will be moving over a scale. This is a scale. Only scale we see, all the things are covered by a cylinder or a cover. This pointer mechanism will be inside. So you see the outside of the pointer moves over the scale. So normally we may have up to 0 to 20 kilogram force, this normal range, domestic spring balance, and with a least count of 0.5 kilogram, we can read up to 0.5 kilogram force. This is very convenient to use measure the household articles. So this is the first foremost elastic element, that is the spring itself is made use of in the form of spring balance. And other elastic element is the foremost and often used is the column type strain gauge load cell. This is very often made use of, and it has got fairly high load carrying high capacity. So few tons, up to few tons we can measure. The main advantage for all these instrumentation is this spring balance is a purely mechanical instrument. Because only static, no dynamic measurements can be made. But in case of this column type strain gauge load cell, we are converting the mechanical signal force into an electrical signal. So you can use it for both static as well as dynamic measurement. Force can be varying, and still you can measure it. As you find, this is typically a second order instruments. We have got a particular, I mean, spring constants. That is the force per unit deflections. So spring is there, and air is the surrounding medium, damping medium, and the mass here will be the force transmitting element. Suppose this is being transmitted by a machine member, that mass also we have to consider in finding out the natural frequency of the whole instrumentations. So the mass of the transducer alone is not sufficient. The transmitting force transmitting member, that weight also we have to add to this machine, to this instrumentation, to this column. So it's a typical second order instrument. Here what you are doing is we take a length for suppose this we are using for a compressive force. When you want to use it for tensile, you have two cups or so whatever it is with the spring with screw threads. You can make suitable fittings and then apply a tensile force. So same instrumentation you can use it for tensile force also. Same column. Here we want to stick strain gauges. So if it is sufficiently large diameter surface area, we need not make the flat surface. You cannot make a square surface inside. On the flat, just on the cylindrical surface itself, you can paste strain gauges. So this may be one. The 2 is perpendicular directions. This is 2. 3 is behind, just diametrically behind this. So so this is our 3. This is our strain gauge 1. Strain gauge 1, and this is 2. Because in transverse directions it is pasted 2 and 4. So 1, 2, 3, 4. These are the. That is, if the column is having, if the cylinder has a sufficiently large surface, then we can paste the strain gauges on surface itself. But if it is a smaller diameter, then the curvature may not allow us. Small curvature may not allow us to paste the strain gauge rigidly. So in that case, we make a square cross sections or flat surface. We machine it and then paste the strain gauges for better bonding. So it becomes, after fixing the strain gauges on the column, then it becomes part of the column. And this column material you have to carefully select. We should reduce the hysteresis effect of the spring material. So some alloyed steel or spring steel with some additions will make a large elastic limit as well as less hysteresis. This is what is important for long time usage or long life. The calibration should not change. So once we know for a column type we cannot paste all the strain gauges along the axis. This we have learnt already under bridge network, the sensitivity of bridge network. So 2 strain gauges along the axial directions, that is the strain gauge loop will be along the axis. Then the other strain gauges it is 90 degree perpendicular to the axial, 2 in axial direction, 2 strain gauges in transverse directions. That will make a 2 into 1 plus mu, where that is the total sensitivity of this instrumentation, where mu is the Poisson's ratio. We learnt at that time Poisson's ratio, where S is the sensitivity of a quarter bridge. So with such instrumentation you will have the twice the, suppose if it is 0.3, then you will find 1.3, so 2.6 times the sensitivity of a quarter bridge. That will be total sensitivity. Higher sensitivity means we can have larger signal output EO. So now the 4 strain gauges are connected in the bridge network, R1, R2, R3, R4. So R1 and R3 axial strain, and R2 and R4 takes the transverse strain, Poisson's strain. So it's called Poisson's configuration. We have learnt already earlier. So it should be like this. If all of them in the axial direction, output will be 0. So to avoid it, we put 2 in Poisson's 2 in transverse directions, and so. Now this instrumentation we find it is insensitive for the temperature variations, because it's a full bridge. All the 4 strain gauges are under the same temperature conditions. So you find temperature compensation is already there. Yeah? There is no dummy gauge. There is no need for any dummy gauge. So temperature, because all temperature brings same effect in all the strain gauges. Any same effect on all the strain gauges will give rise to 0 output we know already. So temperature is taken care of. Regarding the coefficient of linear expansion, that aspect of it. But temperature will affect the Young's modulus of this column material. Yeah? That is, when temperature is higher, then Young's modulus will come down. That is, for a given force, you may have larger deformations when Young's modulus comes down. Then that is to be accounted for. That is done by having a resistance in series with the excitations to the bridge. How these compensate for this change in Young's modulus? Suppose temperature has increased, then Young's modulus comes down, then large strain is there, so larger output voltage will be there in the bridge network. So this we want to reduce it. That is done by having RC in series. This also will be same atmospheric conditions, same temperature. So when temperature increases, RC will increase. When RC increases, voltage drop here will increase. So net voltage coming to the bridge will be reducing. We know the sensitivity of a bridge is proportional to the excitation voltage. When excitation voltage comes down, then the voltage output reduce. If you so select a value of RC, this reduction is equal to the increase due to the reduction in the Young's modulus. So you will find more or less that net may be very small. If they are not equal, it may be very small, so error may be within tolerable limit. So that is for temperature compensation. For change in Young's modulus, we put a resistance in series. And you will find one more advantage of this instrumentation is this will be sensitive only for this axial loading. Suppose there is a bending moment due to some eccentric loading. Suppose it is here and you apply like this. So you find a small couple or moment is there. In such situation, what will happen? This one will be, suppose it tilt in this way. So one will be in tension, and 3 is opposite phase. 3 will be in compression. Now 1 and 3, they are subjected to opposite strains, and that means they should be put in adjacent arms for maximum sensitivity. But you find they are put in opposite arms. So opposite strain in opposite arms gets nullified as per the rule of the bridge. So even if there is bending, there is no output due to that bending strain. Similarly, if this way, if eccentricity is there, and 2 will be in tension, 4 will be in compression, and 2 and 4 on opposite arms, an opposite strain gives rise to 0 output voltage. So you will find this instrumentation is insensitive for both bending load and temperature effects. So that is advantage, but one should be careful when we design this column. Column height should be sufficiently short so that under this compressive load it doesn't buckle. That's one thing. Secondly, the place where we are going to fix these strain gauges should be sufficiently weak, or it should, it's sufficiently weak. Okay, sufficiently weak to produce sufficient strain in the member. If we fix the strain gauges on the existing member which has been designed for strength, then you will find the strain produced will be very small of 0.1 or 0.2 micro strain, which will not give rise to any output voltage. So when you want to fix the strain gauges in existing member, at that place you have to weaken it so that there is sufficient strain, but you should not weaken in a way it goes to plastic region, but still the loading range should be just above the elastic region. So it will produce at least a 200 micro strain. That is what we expect, microns. At least 200 micro strain should be there for the maximum loading. If it is 0.1 or 0.2 microns, then it will not produce any effect. So you find for this load cell where we want to fix the strain gauges, there should be sufficient strain. To that extent, you have to weaken that place and then only fix the strain gauges. This is what is important. So here you find in the column type, the spring constant, since it is solid member, is fairly large, and that is deformation will be very small, to have some more sensitivity. But advantage is, since Ks is large and the omega n, which is root of Ks by m, will be larger omega n, so it will have naturally larger bandwidth. But the problem here is, since it's a column, it may have the smaller deflections, or sensitivity may be small. To increase sensitivity, what we can see, one disadvantage when we reduce the cross section, then it becomes too narrower, or you may have very small area for the strain gauges. To avoid the problem, what people do, you can have a hollow constructions at the place where we want to fix the strain gauges. Have the hollow constructions, small wall thickness, so inside it will be hollow, so that you find it is weak, at same time sufficient area is there for fixing the strain gauges. So all these measures we can observe, so that sufficient sensitivity it comes. But another better design is going for the proving ring transducer. Here we have much more sensitivity than this, but problem here is Ks, spring constant is reduced and bandwidth is reduced. So this is always the case in instrumentation. When you want to increase one characteristic value, and some other characteristics gets affected. That's why you have to come to a compromise. Anyhow, this proving ring load cell or transducer is widely used in places, industries and laboratories. It is made up of just a ring on the surface of the inside and outside surface and surfaces. We paste the force strain gauges as it is shown here, and this is the end view of it. So you find when the load is applied, it is compressed, the ring is compressed. So this compressive load converted into bending strains at the surfaces 1 and 3 will be subjected to tensile strain, 2 and 4 will be subjected to compressive strain. Then the same bridge holds good, 1 and 3 in compressive, 2 and 4 in tensile, 1 and 3 tensile, 2 and 4 in compression. So some bridge we can use. Again you can have this compensation for elastic modulus change due to temperature. So same circuit you can use it for this, and also advantage is here more sensitivity, and but the load capacity is reduced. So if probably 1 or 2 ton. Here we may go up to say for 50 or 100 tons we can go for column type. Here it is a small little bit reduced. The disadvantage of this setup is if you unknowingly load more, then these points may go into plastic deformations. It may not come back to original, because we might exceeded the elastic limit. That is danger. To avoid this, we have some other design. Yeah. Here is a load cell with overload protection. See here, this special construction with a gap S. So in one circle, we have got 2 circles with the central gap. So when you put the load here F, so this is a fixed surface. When it is compressed, and when the gap is reduced to 0, any further loading will go to the floor or the ground directly. It will not stress or strain the elastic member. So until it becomes 0, you have got strain here, it will be within the elastic limit. So you find beyond elastic limit, the force will go not through this element but directly to the floor through this bulging. Yeah. So there is a protection, overload protection here. So if you want to have still smaller, higher sensitivity and smaller for smaller load range, the natural cell, it's a few gram onwards we can measure by having the cantilever type of load cell. Yeah, say it's written is cantilever transducer, but cantilever load cells. This we have made use of for explaining many principles, bridge network principles. We have used this example very often. So you find at the top surface 2 strain gauges, 1 and 3. Same bridge network, whatever you learnt earlier, same thing holds good. So this is 1, 2, this is 3, 4. That is 1 and 3 will be in for this type of loading. It's tensile strain. 2 and 4 will be in compressive strains, and 2 polarity we have got. So all the 4 will give rise to 4 times sensitivity of a quarter bridge. So this is a full bridge, and temperature compensation is there. And for accounting for the Young's modular change due to temperature, we connect RC. Same circuit we can have it. So this is for smaller load range. We can go for this cantilever type. By having the different thickness and a different length, we can have different load ranges in this. It's a very versatile, useful principle. Then next one is using diaphragm and using LVDT, diaphragm type of load cell. So 2 diaphragms are there, and at the middle of the diaphragm one rod is connected, and at the end of the rod we give the force which we want to measure. It is supported in the, say it can be supported on the floor. Now give the load, and the diaphragms deforms like this. So this deformation is maximum at the middle. So the rod comes down. At the bottom end of the rod we connected the core of an LVDT or of self-inductance pickup. Here it is LVDT. So this is your supply voltage, 2 secondary connected in oppositions. So the output voltage EO is a modulated voltage, a modulated signal, modulation between ES and the magnitude of the displacement of the core. and further we process it as we learnt earlier in LVDT by giving amplifying or without amplification given to phase sensitive demodulator and low pass filter, and finally we get a displacement, this displacement there. That displacement is written in terms of Newton or the so many Newton or kilogram force. That is how the displacement reading is converted in is calibrated in terms of force unit. So here we have two transducer, one to transduce the force into deformation and this deformation back to voltage. That voltage is written in terms of Newton. So two secondary two transducers in essence. Here, that is the case in almost all the type what we are the elastic members with strain gauges. We use one member, elastic member, to transduce the force into strain. That is the block diagram. That is the force converted into strain. Force converted into strain, either in the cantilever or in the proving ring or in the load cell. We use that primary. This is a primary transducer load member. So this is to be properly designed so that sufficient stress and strain is there. And then later on we give this to a bridge network. That is our bridge network. And from there we get an output voltage. This is the instrumentation. This output voltage is further amplified or read according to the situations. So two transducers, more or less you will find two transducers are there, epsilon to E0. Either the LVDT or strain gauge, anything we can use. The one problem in the cantilever type of transducer is, suppose this is load button, this place where you are supposed to apply the load or force. If it is little bit changed, it's a little bit changed, then you will find for the same force little bit earlier in this cantilever, you have the less strain here. Then the instrument will show a less reading, smaller reading. The force will maybe 10 or 100 Newton, but the instrument will show only about 90 Newton. It is because it is shifted from its original place by due to some error or something like that, little bit earlier. So to that extent the instrumentation gives rise to that is, it is very sensitive to the proper placing of the load on the instrumentation in the load cell. That problem is solved once you go for the shear type of load cell. Here you can apply it here or here, nothing will happen. It will give the same reading. It is non-sensitive for the location of the load at the more or less it is this loading point. So about the loading point, if you vary, it's not affecting the instrumentation. Where it is in cantilever type, it is very sensitive for this small error in putting the load, applying the load. How it is non-sensitive? It is because this instrumentation based on shear type. We know the bending moment diagram for this cantilever is, it goes like this. From tip is 0 bending moment, and at the bottom is the near about fixed end, you got the maximum bending moment. It varies linearly. Whereas shear force diagram for this cantilever, for the same cantilever, shear force diagram is rectangle. Shear force diagram is rectangle. From this point to the up to the fixed point, shear force remains same. It is same as applied load. That means shear force doesn't change with the distance of the application of the load. So that is the property what is made is aware. Load is applied here F, and we know shear force is same throughout. So you can select any place, but here you have to be careful because from shear force we have to go for the maximum stress or strain, that is principal strain, the compressive or tensile strain, that is at 45 degrees to this axis of this one. So the if the one, then the other one at the back side you can put 90 degree to these orientations. So that will be dotted line I am drawing. So it will be like that. So if one is in tension due to the shearing in this axis, so compressive tensile will be available 40 degrees to this one which we have learnt in machine design. So one will be in tension and two will be in compression. Then you connect. So in the same bridge, one is in tension, this is tension, and the other two is in compression. So adjacent terms you connect, and if you want 4, 3 also, you can 1 and 3. Same way you can have another parallel, and you can have 4 strain gauges also. This will be 3. Behind that, for 90 degree to that, it will be 4. So that full bridge. If 1 and 2 alone, off bridge we are making use of. So that problem of loading at exact place, or if you make this is an instrumentation which is not sensitive for the loading point. So it is nowadays very often used. Shear type load cell is often used. And the next what we are going to see is 3-dimensional load cell. Suppose a force F acts in some random direction like this. these are random directions, which a component which Fx, Fy and Fz along the 3 coordinate axes. This is 3 dimensional one. So it is not vertical or horizontal or x direction or y direction, so some random directions. So for that we use a column like this. This column should be a little bit sturdy or a strong column, because due to this application, if it bends, it gives rise to a lot of error. So the amount of deformations should be limited. For that, to that extent, you have to have a strong beam fixed at the bottom end. Now the Fx and Fy, they will bend the beam having a cantilever at the having fixed end at this bottom. The beam will function as a cantilever for Fx and Fy. For Fz, it is again a column. We know instrumentation for bending. For bending top surface 1 and 3 tension, bottom surface 2 and 4 compression. Similarly, if you consider Fx when it is act this way, this layer will be under tension, the other layer will be, bottom layer will be under compression. So x1 and x3, x1 and x3 are in tension, and y2 and y3, y2 and y4 are in compression. I mean x2 and x4 are compression. So I have drawn one bridge network, and I am supposed to draw 3 bridge networks, for one for x, another for y separately, but nomenclature will be more or less same. That's why I indicated here. But we should have 3 independent bridges, one for x instrumentation, x direction, and another one for y instrumentation, and another one for z instrumentation. 3 bridges we should build for each component force, and this is EOX. You will have EOX from the x bridge, and EOY for the y bridge, and EOZ for the z bridge. So 3 different bridges. They are added finally in algebraic fashion, and the final output voltage will be proportional to F. So algebraic addition of these 3 independent voltages from 3 bridges will be proportionate to the final force, 3-dimensional force F. But we should be careful. The instrumentation for x direction Fx should not be influenced by y direction force, or the instrumentation, the strain gauges meant for Fy, measuring Fy, should not be affected by the Fx. That is possible only when you fix the strain gauges so about the neutral axis, symmetrical distance from the neutral axis. For example, you consider this face ABCD. This is the face, and the neutral axis more or less at the middle. So you find y1 and y3 will be equidistant from the neutral axis. In that case, the error, in that case you will find the instrumentation for y will not be affected by the force, the other 2 forces. For example, you can see Fy, y1, y3, and Fx is this direction. So you find this is above the neutral axis. y1 will be in tension, y3 will be in compression. y and y3 should be in adjacent terms for Fx, but y and y3 are in opposite terms. y1 and y3 are opposite terms, so it gets cancelled out. Similarly, you can analyze in all the strain gauges. So Z1 is at the middle, and you will find top side will be in tension, and bottom side of the from the neutral axis compression. Within the strain gauge itself, it gets cancelled out. So instrumentation for one direction force will not be influenced by the other direction, provided the strain gauges are fixed symmetric about the neutral axis on each face. So for Fx and Fy, we have got 4 strain gauges. Similarly, for Fz is column type, so you cannot have all the 4 axial directions. So here we have the 4 times sensitivity for Fy and Fx as the quarter bridge, whereas for Fz we have the 2.6 times the sensitivity of the quarter bridge, because it is the axial force. So 2 in axial direction, 2 strain gauges, other 2 strain gauges should be transverse in Poisson's configuration. So sensitivity for Z will be little small, does not matter. We calibrate in terms of the we are going to add these forces, and then later on we are going to calibrate. So this is the way, all the 3 components, and finally we add the output of individual bridges and get the signal proportional algebraic addition and get the signal proportional to F. Next we see the piezoelectric force transducer. We know the piezoelectric crystals, and they respond to dynamic loads. So we can have this piezoelectric crystal apply the load, either give displacement signal, or we can give force signal also. Displacement signal alone we cannot give without a force, because the crystal will not deform. It has got very high spring constant. So now we use it for measuring force. So apply the force, then it deforms. The deformation is producing a charge, and that charge we take it to a charge amplifier. This can be taken to a charge amplifier, and just to the charge amplifier, and the voltage output can be read there with the help of a voltmeter. Yeah. So instead of displacement, we can use it for force also. Known force, calibrate the readings, and later on allow the unknown force to act, and then you can from the calibrated curve we can find the what is the force. As we know, this crystal can be used only for the dynamic load, that omega being between say 3.04 over tau and 0.2 times omega n. That is for 5% error, plus or minus 5% error, and also when psi is equal to 0. That is, crystal works more or less air damping can be assumed 0. So you will find under these conditions the bandwidth for this instrumentation is 0.4. Tau is the time constant of the electrical circuit, 3.04 over tau. That is, it functions like a simple capacitor transducer, because fixed this is a metallic plate at the bottom and at the top. So this is a dielectric medium, insulating material. So it is a typical capacitor circuit. We already learned 5% error. Omega should be larger than this value, 3.04 over tau. And considering second order system, we have found out it should be less than 0.2 omega n for 5% error, psi being 0. This all we have arrived already. So this is the working range for this piezoelectric transducer. Otherwise, it is a very good dynamic measuring instruments, a force measuring instrument. Second, next method is force by acceleration measurement. Force by acceleration measurement. That is, a member is there. This is a machine member, and we want to find out what is the force acting on this member. So we can connect a load cell and find the force, but in many instances it may not be possible to connect to bring a load cell here. So people, what they do, they put an accelerometer here. So they will measure the acceleration A, and now we know force F is equal to, if m is the mass into acceleration. So by measuring the acceleration and knowing the mass of the body of machine member on which the force is acting, we can find out the force. It's indirect way of measuring. So by measuring the acceleration, we measure actually force. But what is the drawback in this? It will measure only the resultant force. Suppose there is friction force, it is moving over a surface. Suppose there is friction force Ff. The net force is F minus Ff. Now instead of F, it minus Ff. F minus Ff will be equal to Ma. That means you should know the friction force. If you do not know the friction force, you will be assuming that to be force, so that will be error. So you are measuring a smaller force, but you will be calibrating as a bigger force. Suppose you have 10 Newton and here 1 Newton, then only 9 Newton alone accelerate this mass. So accordingly, acceleration will be smaller, and that you will be writing it as 10 Newton, because you do not know the friction force. So that is the error component. So that means the acceleration will be proportional to the net force or resultant force, and you cannot find out the component of the resultant the different forces constituting the resultant force. So this instrumentation you can use it only when the resultant force is 1, or if there is another force, that force amount should be known to avoid the error in the measurements. Drawback is the acceleration is a result of the resultant force. That is the point what you have to measure. The next what you are going to measure is closed loop instrument. It's called electromagnetic balance. That is electromagnetic balance. What I written here, electromagnetic balance. This is a closed loop instrument. Yeah, it's a closed loop instrument. So far what you have seen, all these instrumentation, earlier version whatever you have seen, they are all in open loop instrumentation, but now it is a closed loop instrumentation. The general advantage, whatever it is there in closed loop instrument, it's here for this instrument also. That means they have got higher accuracy. Higher accuracy, say 0.1% accuracy you can get, whereas in open loop we can get 1 or 2% accuracy alone we can get inaccuracy. So it is functioning like this. Force is this is one of the versions. There are many versions. One of the versions of such instrument is we have got a lever at the end of which we apply a force F, and the other end we have got these inductive pickups, and the this is a force coil. Here we can call it a force coil. This force coil are arranged. The functioning is like this. We can explain with the help of the signal flow diagram also. We apply a force F, and at the end of a lever, this is a lever, so a moment is there. That moment, say Mi, this is Mb. There will be some force on the force coil that is acting at a distance, so there will be some Mb. The resultant of these two moments is Me. Me acts over this coil spring. This is a coil spring. So that moment is converted into angular rotation theta, that is theta. Yeah. This theta at a distance of another distance we have got a pickup at the some other distance. So theta times the distance will be displacement at this tip, that is this is the tip, displacement, inductive pickups for measuring displacement. So that much displacement will be sensed by this pickup, and it is given to the carrier frequency amplifier. The current will be flowing here I. Yeah, due to this current. This current is taken to the force coil. The force coil gives rise to a force bringing the lever back to its original positions. So the amount of current required to bring it back, it's a measure of the force. If force is larger, it will tilt more and it has to be brought back, a higher current will be going. So the amount of force required in the coil to bring the lever back is a measure, and proportional to that force you have got current flow in this system. So you find a current flowing through that constant resistor R gives rise to a voltage drop UO. So that is why it is taken here. So I flowing through R gives rise to UO with this output signal, and this I is taken to force coil to give the feedback moment. So now EO read in the read here with the help of voltmeter can be calibrated in terms of force here. So that is how the closed loop instrument is functioning. Any error, any temperature rise and will not affect this instrumentation accuracy, because if a coil resistance, coil spring constant is changed due to temperature, the same coil resistance same spring constant is valid for the feedback also. So that softening of the spring will not, because softened spring will require only a less force here in the coil also. So you find it gets stabilized. This error source gets nullified. So that is how it is having a larger accuracy. Yeah, we will close it at this point.